A little wide. Oh, that's really wide. I mean, it's fine. It's just funny.
Yeah, I mean, but is this appearing okay, or is this also appearing white?
No, that's fine.
Okay, okay, yeah, that's what the monitor is white, so I wasn't sure about that.
Yeah, I do have a wide monitor at my office. It's very nice. I think we can get started.
Okay, cool.
Yeah, so welcome to one of the second Carper talk of February. We have Karthik today. Karthik is an NLP professor at Princeton, who was actually also the reason why I got into NLP, some of his early papers on like text adventures and reinforcement learning. And he is somewhat interested in one of the earlier directions that Carper was taking on applying natural language to rewards and using like critiques of like written text as a mechanism for improving said text. So we thought it was particularly relevant to invite him. And yeah, so here we are. Karthik, if you want to take it over.
Sure, yeah, thanks, Louis. So yeah, thanks for coming, everyone. I'm calling this language-guided machine learning. I'll sort of try to give an overview of some pieces of work that broadly fall into this, but happy to discuss more. So feel free to stop me at any point too. I can see you, so if you raise your hand or something, I can definitely stop. So right, so as you have seen, there's the word language in the title here, so I feel like I'm sort of obligated to start off with some kind of ChatGPT example, right? I'm sure all of you are aware of ChatGPT's capabilities, right? It's pretty impressive. It's a great language model. But so when it was first released back in November or December, I guess, I still remember I was in Europe, and one of our undergrads in the NLP group, he got a chance to try it out early on, and he just asked a simple question, what do you know about the Princeton NLP group? And on the surface, it looks like decent text, but if you read through the lines, right, obviously it has fake information, things like Chris Manning, who we'd love for him to be part of our group, but he's not. And it also says things like we developed the standard parser and NER system, which are obviously wrong facts. And he sort of probed it further, but as you can see, the system sort of sticks to its guns, right? So it's not really getting a chance to fix itself in some sense. And so you might ask me, okay, that was back in December. OpenAI has put in a lot of effort into fixing these kind of issues, right? And so I tried it again today and asked it exactly the same question. What do you know about the Princeton NLP group? And unfortunately, it continues to fail, right? So now it just gives a different list of people. Again, folks that we'd love to have as part of Princeton NLP, but you, Percy, and Claire are not actually part of Princeton. And a similar thing sort of occurs, right? Like, so even if you sort of probe it further, it still gets wrong information, which to my knowledge, I don't think you have Percy have been affiliated with Princeton at any point. So why am I showing you all this? I'm sure you're aware, ChatGPT makes mistakes, other systems also make mistakes, but I sort of want to talk a little bit about what are the ways we can try to fix these kind of mistakes, right? So the sort of really expensive, naive option is you just try to retrain the model, try to be smart about how you handle data, maybe figure out different ways of, emphasizing factual knowledge, things like that. But that's not really going to fly, especially when we're training really large models. The second kind of option is to use some form of human supervision to fix errors and guide the model, right? So this can be sort of, the latest and greatest things like RLHF, right? So getting people to sort of tell the model what is right, what is wrong, and then use that to fix the model itself. There is a third option, which which we also have some work on, but I won't talk about it. But you could, for example, think about dynamic retrieval of facts, right? So you have a knowledge base such as the web, or a database or something like that, and you can integrate things into the language model such that it can retrieve these kinds of facts. But in this talk, I'll sort of focus on the second kind of thing, right? So one way we can try to fix these things, and in general in machine learning, try to guide models, right, is to use human supervision. And the sort of the trendy or most popular things right now are, you sort of get humans to annotate or provide labels for certain tasks, or you can also use things like RLHF. But what I want to sort of focus on this talk is that while those things are great, they don't really scale up well, right? So you can give bit points of information, like for something like RLHF, you're giving 1 bit information.
Sorry,
it's better than this or something like that.
Someone's mic is echoing. Who is this? Whose mic is echoing? Okay, I think that's resolved. Sorry, continue.
All right. Yeah. So so basically, what I want to show you here is, right, if we actually use more interesting forms of guidance, like specifically language guidance, we can think about having a higher bandwidth way of training these models, right? And so just to take one step back and also look at these things from the other side, if you have been working in NLP, right, over the past few years, especially with the advent of deep learning, right? So there's been sort of the shift in how people treat NLP, right? Like, so basically modern ML is basically treating natural language as yet another modality, right? So we have models like transformers, RNNs, graph neural networks, and your favorite new architecture. But the sort of procedure to train these models is pretty much the same, whether you're doing things like computer vision or NLP, right? So you sort of take standard gradient descent techniques and so on, apply it on a data set, annotated data set, and you sort of get results on the tasks that you care about, right? So there is a need. So on the one hand, there's sort of a need for better ways of guiding and training our systems. And I'm saying that natural language is one way to do that. But on the other hand, in NLP also, right, there is this question of, can we use natural language for something more than just a modality, right? So in the other direction, what can natural language provide for benefiting the process of machine learning itself, right? And so in this talk, I sort of want to focus on this point, right? And show you different ways you can use language, right? And integrate it into parts of the machine learning framework. And I'll show you how that can provide us many different kinds of benefits, right? So including generalization, control, safety, and so on. So very specifically, right? So I sort of want to talk about language as being a nice medium to provide more semantic forms of supervision, more high bit bandwidth forms of supervision, and also a way to provide, an easy way for humans to provide guidance to AI or ML systems, right? So, and this is particularly important if you want your systems to learn efficiently or learn safely. Why you would want to do this, again, right? Like there are nice properties, but also it's very easy to for humans to communicate in natural language, right? So that's something that we all take for granted, including me giving this talk right now. I'm taking it for granted that you can understand me perfectly well. Okay, so like I said, I'm just going to talk about a few pieces of work that fall into this, and each of those is going to use language in a different way and try to integrate it into standard ML frameworks that you're all familiar with. And so let me start off with the first one, right? So if you just take the standard supervised classification setup, right? So you're basically trying to classify some sort of input. This can be something like text or image or whatever source that you're wanting to perform classification on, and you're trying to predict some outputs, right? So these are usually some predefined classes, and you assign them class IDs, right? Something like 1, 2, or 3, and you're basically trying to learn this function. The machine learning model is basically the classifier is a function f that's trying to go from x to y, right? So given any input, I want to generalize to to predict the y for any input in my test set. that is going to be a different set that I'm not going to see at train time, right? This is all great, right? There's a lot of learning theory, statistical learning theory, all sorts of things around this. But one specific limitation here in this setup is, the output space of this function is limited, right? So you can only predict over the class IDs that you've seen during training, and you can never try to predict a new class, even if it's very, very related to the classes that you've seen, right? So this is our standard classification setup, something that you've learned in when you first maybe got introduced into ML, right? So if you think about this in a sort of like a multiple choice question answering manner, right? What this basically alludes to is we're basically asking the model to answer these kind of multiple choice questions, given an input, which choice is the correct choice. But the point here is that all the choices are fixed numbers, right? They don't have any semantics on their own. We're abstracting all of that away and training the model to do that, right? And that's why it makes sense that it can only predict one of those choices given any input, right? Regardless of whether you've seen this before or not. So this is not really suitable for generalizing over predictions in your output space, right? So you're sort of bound to these choices, which are basically just integers. And so you can imagine what could be an alternative, right? So for a human, like if you take something like an SAT or whatever, right? Like some standardized tests, nobody's going to give you just 1, 2, 3 and ask you to predict, right? So usually when we think about multiple choice questions, you're basically given choices that are more semantic, choices that can be read and before you pick the appropriate choice, right? So in one way, you can think about something like image classification, right, as basically having these different class choices where you have some description of the classes themselves, and you can sort of allow the model to read these different options before picking one of them, right? Now, why is this a good thing? There's several reasons why you may want to do it, and you may already be thinking about some of these, right? The first thing, of course, is that you can freely vary the number of classes, right? So you're no longer limited to the 1, 2, 3 that you trained on. You can, for example, throw in other new classes, as long as the model can sort of understand, the words that you're specifying for each class and use that to make a decision, right? On top of that, you can also change the way you describe a particular class, right? So if you want to make certain small changes to how you describe a tiger, that's perfectly fine. The model can adapt. So tomorrow, if a definition changes, for example, for a class, you can just change the definition in your particular classification setup, and you don't really have to retrain the model or anything like that. You can also, this is sort of something that's been explored a little bit in prior work, right? You can also describe new classes in terms of known concepts, right? So this is a more straightforward advantage here, right? So you can describe something like zebras that you've not seen before, or you can even describe imaginary concepts like unicorns or something like that, right? In this particular case, as long as you're using words that the model can understand. And finally, you can also basically redefine how you think about the cloud standard classification task. You can have classes that span different levels of granularity. For example, if you want to, classify between a reptile and an elephant, that's perfectly okay, right? So you don't have to redefine your hierarchy each time you sort of specify a different problem, right? So in some sense, what this is allowing us to do is taking away the pre-specification of the output space and just saying, okay, anything that can be described in language, you can make a new partition and define your new task. And as long as you're able to map from any input to this language space, you should be able to generalize to new tasks which have new partitions in whatever way you define them and choose your classes. Okay, so this is basically what we set out to do, right? So we wanted to make as little as possible a change from the standard setup. So we introduced this framework, this generalized framework that we're just calling semantic supervision. This was work led by a couple of my students, Austin and Amit. And the high level idea is basically just that, right? So in the standard setup, you have some kind of an input and the output space is just these class IDs. But we ask a question, what if we provide more semantic information on each class, right? So this can be, for example, descriptive targets like text. This can also be other things that can be used to describe, the different classes. For example, We also experimented with something like JSON, right? So you could specify important properties about these different classes in JSON and so on. And the nice part here, which I'll show you very soon, is it sort of allows for generalization over both inputs and as well as the outputs, right? So you can freely change what you're defining as your set of classes without really having to bother about retraining the model or making sure it can conform to the new test. Okay, so that's the high-level setup. So how do we actually train a model for this? That's also pretty simple. You can just think of it as basically having two sets of encoders. You can think of an input. Again, the input can be anything you want, right? Like text or images or time series, whatever you want. You need some sort of an encoder that can encode this input into a vector representation, because that's what most neural networks are good with, right? And then for the output level, right? So we basically provide multiple descriptions for each class. One particular description may not be sufficient to describe an entire class. So we have multiple different class level descriptions that we can just sample over. So what we do is, for each of these classes, we sample a few descriptions and then encode each of them to provide, a vector representation for each class, basically. So just like on the input side, you can do a similar thing for the output side. So now we basically have one vector for the input and a bunch of vectors for the output themselves, output classes themselves. And then, I won't go into details here, but there's different ways you can sort of score the similarity between these. You can use a simple bilinear function. You can use something slightly more complicated, which involves a combination of lexical and semantic similarity functions. But we can sort of basically determine what is the score for each of the classes given my input and my output encodings, and that can give us basically the logits for each of the classes, right? So and we can do a very similar thing for different kinds of things. So if you have something like an image, right? We have an extra thing that tries to use it for lexical similarity, but the high level idea is the same, right? So you basically can use an encoder for the input side and output side, regardless of whether it's text or JSON, and have some sort of similarity metric that can give you logits. And you can train this entire system just like you would do for a standard supervised learning model, right? So you don't have to do much more than just get the descriptions and encode them. Okay, so based on this, right, so I'm sure some of you are already thinking about some piece of related work. So I just want to put it out there, and if you have other questions, ask me. So this might remind you of work like Clip, right? So Clip is this model from OpenAI, which basically takes images and their captions and tries to embed them together. This is not quite the same because for one, we're not talking just about text and images, right? So it's not a multimodal thing. We're just saying take any classification problem, just replace the classes with the descriptions and do exactly what you're doing before, right? And you will get some very nice properties out of the box. And so Clip is sort of like you can think of one instantiation of this whole framework, right? So you can think of, if you think of each caption as being its own class, then yes, it falls into one specific variant of the SEMSIP framework that I just described. And so you can think of it as a special class. And the second thing that I want to say is, you could also probably think about connections to language models like T5 and talk about how this compares to prompting language models, right? So you can think of having some sort of an input, and then the output, of course, is a text, right, that refers to some class. So the sort of difference here is, again, you have to make a lot of adjustments if you want to convert your classification task into something that works with T5. For example, you need to prompt it well. You also need to define the output space, right? And T5 can generate tokens, so you need some way of scoring tokens. And this becomes quickly very, very hard if you have a long description of a class, right? So if it's one or two tokens, like sentiment analysis, yes or no, should be fine. But this sort of gets quickly difficult when you have more nuanced classification tasks. So right, so basically, they are related, but I sort of want to emphasize the simplicity of what I'm trying to talk about here, right? So when you just take any supervised classification task and you can turn it in just by simply collecting descriptions for these classes. Okay, so let me just give you a quick idea of what we did in terms of the experiments, right? So we tried it on a bunch of text and image classification data sets. How did we get the descriptions themselves, right? So this was fairly straightforward. Didn't take much time, given that you're doing it once for a data set. We just converted class names and queried web search engines like Google or DuckDuckGo, and you can just automatically scrape the sort of descriptions that you get from the search engine results. And we have to do a little bit of manual filtering to remove, ambiguous descriptions. Sometimes the model, the search engine may result in a different notion of the same word, and so we have to do this manual filtering. But then once you're done with that, right, you have pretty good descriptions. And for something like JSON, you can just use sort of attribute sets to automatically create, a sort of an entry for each class. Using keys and different attribute lists as values. So here's an example of how this looks, right? So take something like, the class of consumer prices in RCV1, right? This is how the text would look, right? So it's basically something that was scraped off of a website. It's a price index. So this is sort of easier to understand. A more structured form of this would include the definition, right? So I think this is from WordNet, as well as related terms, right? So you can use a structured database like WordNet or Wikidata or something like that to get these kind of structured information. And so the basic idea is like we're going to use these more semantic information per class, and then train our models on them. Okay, so before I talk about the nice transfer properties, I just want to first point out that SEMSIP is actually a straightforward drop-in replacement for standard classification, right? So we want to make sure that if you're replacing your classification problem with this, you don't lose anything. And this graph is just basically telling you that, right? So if you have a standard supervised model, which has these gray bars, across all the data sets, you don't really lose much. You lose a little bit on CFAR. I think there was a little bit of noise in the descriptions for that particular data set, but even that is just a couple of points, right? So across the board, you're basically having the same level of performance if you're training and testing in distribution, right? So you don't lose anything in terms of generalization to in distribution data. But on top of that, you get things for free, right? So like I mentioned or alluded to earlier, you can get zero-shot generalization to a lot of things without really doing fancy tricks, right? So you can generalize to unseen descriptions, unseen classes, unseen superclasses, and all of these, all we have to do is simply change the descriptions of the choices that we provide to the model, right? So we don't have to really change anything in the model at all, and things sort of, the model just gives us some nice transfer properties. So yeah, let me just give you a sort of snippet of these results. There's more in the paper, you can go look at it. But this is sort of generalization to unseen descriptions. So you can see here, we have a few baselines, like for example, this is clip-RT5 depending on the task. I forget which task. Oh, okay, this is average over 4 tasks. So if it is a vision task, we use clip, otherwise we use T5. It's sort of like zero shot, just to show that even if you have a large language model, you're not really doing large model, you're not really doing well, large pre-trained model, right? And so, right, so it doesn't do well if you use like simple bioencoders or prior work like Guile, you sort of get up to 70s and so on. But if you're using multiple descriptions and using that in this particular SEMSIP framework, you can actually get much better generalization to unseen descriptions. And a sort of similar thing holds for unseen classes and superclasses, basically. So if you introduce new classes, the SEMSIP model gets better scores than some of these other baselines. And a similar thing for superclasses, where the example that I showed you, right? Like you want to classify between, you train your model on low-level classes, but then you sort of test it on superclasses, which are one level up in the hierarchy itself. Okay, and then one final point was we also sort of did this ablation. Do more descriptions actually help? That is actually true. I want to keep things simple here, but you sort of see this nice curve where the more descriptions that we use on the x-axis 1 to 10, we see gains in performance basically. So this sort of shows that the different descriptions are providing complementary views of each class, and that is something to have that is useful. Okay, any questions on this point, or should I just carry on? Okay, I don't see anything on chat either.
I think
All
we're
right,
good.
great. Okay, great. So yeah, so far, I've shown you on more of these standard classification tasks and shown you how Samsip can help, right? And so we thought a little bit about, okay, what is a really challenging classification task, and would something like Samsip actually help in that particular case, right? So one particular paradigm that we found that would be that's quite challenging is something called extreme classification. I don't know if you've heard of this, but this is this sort of task where you have a very, very large number of classes. It's not your run-of-the-mill 5 or 10 classes. You have up to 1 million different classes, and you usually have a rapidly changing class set, right? So think of things like search engines or product tags on Amazon or something like that. So that's what would be some sort of classification task that would fall into the setup here. So we consider the setup of zero-shot extreme classification and try to apply exactly the same Samsip framework that I showed you. We had to do a few things, right? So we use contrastive learning to scale this thing up efficiently. And then we also came up with a way to automatically collect descriptions, because doing it manually for 1 million classes is not going to scale. So we traded off some sort of noise in the descriptions itself, but with some heuristics, you can still get some good descriptions for the classes. And what you saw was, we can actually achieve pretty much state-of-the-art results on extreme classification. So this is a paradigm that people have been working on for the last few years, right? They have different sorts of approaches and different ways of encoding hierarchy and things like that. But all we did was just collect descriptions of these classes, and out of the box, it gets a precision that's much, much better than even the state-of-the-art models, right? And similarly for something like recall, right? So this is a multi-label, multi-class problem. But similarly for recall and for precision, right? Without much work at all, we're able to get a pretty high sort of performance here.
There's a question, by the way. So an average of 5 descriptions for images gives 90%, right?
Average of 5 descriptions for images. I'm not sure which one you mean here. Are you talking about this? Right. So this is actually over all 4 data sets. So this is an average over 4 tasks, 2 of which are text and 2 of which are vision. But I can get you individual numbers afterwards if you want. Okay. So right. So this was like sort of basically out of the box, right? So we didn't do too much, and it also turns out this helps for even the few shot case, right? So if you have a few instances,
there's another question, by the way. Sorry.
Oh, okay, yeah.
Jason.
So if could we go back to the previous slide just really quick?
Yeah.
With those 2 graphs, yeah. So how should we understand? Like, what's the kind of zoomed out view of what this task would be? Is it like a sentence, and then that can be one of 13, or it can be one of a ton of different classes?
Yeah, so you can think of it as a document. So one example would be, let's say you have a new product that you put on Amazon, and you want to tag it with different tags, right? And you have 1 million tags, and some tag can be electronics, something can be things like that, basically.
And so in this case, the part where we're coming up with multiple descriptions for each class, it would be like if there's one tag that's like kitty litter, you would also encode like cat litter and cat litter box powder or something. Like you'd come up with multiple different ways to say each tag, and that's what's
no. So it's more like for each class. So for each tag, you just get multiple descriptions of that tag. So if you have something like cat litter, one description may be like cat litter is useful for blah, right? And then something else might be cat litter is made up of blah, right? and you just describe it in 5 different ways, for example, right? And that gives you a representation of what that class is about or what that tag is about.
Okay, and then you embed those descriptions into the space that's the shared space with the long description for an individual product, and it's some kind
Yes.
of like spatial. Okay.
Yeah.
Very cool.
So do you do hard negative mining for this or not at all?
For this one, not at all, but that's an interesting question. Yeah, we just use randomly sampled negatives.
And why, do you have any idea why sentence transformer does so poorly?
Good question. I don't know actually. I mean, so remember, the sentence transformer is a baseline that is worse than these models, but what the sentence transformer is doing is just representing the document, right? It's not using, so none of these are using descriptions of classes. Only the red one is using descriptions of class.
But what if you just fine-tune sentence transformers on the descriptions of classes?
But that's basically what we're trying to do, right? Like, so you can use any model as long as you're using description of classes, but these models don't use that. They're sort of adding in metadata in different ways and so on.
Okay, that makes sense.
Okay, cool. So yeah, you know, a similar thing holds for few shot. So this is sort of like 0 shot. That's why the numbers are not close to 100, right? But if you do sort of few shot with the same thing, right? Like with just one example, it sort of goes up, and as you add more examples, all of these models start to get better than you know, baseline performance, something like TF-IDF retrieval, right? But you can see that even with that, right, like the sum subset model gets even better than the baseline. So it does learn from this extra information and can continue keeping that advantage.
How are you doing few shot prompting with an embedding model?
So few shot is basically, when I say few shot here, you're giving some examples of the test class, right? That was not seen during training. And you can just train the model on this few shot. It's not prompting necessarily, it's just you're fine-tuning with a few examples.
Got it. Okay, that makes sense.
Yeah. Okay, cool. So let me give you an example of what happens, right? So Montclair is this previous state-of-the-art model. You know, if you have a document like this, right, startup, technical guide, blah, 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 recommends this book to prepare, right? So our model was able to predict it as a new or a used and rental textbook, right? So it sort of has these tags, which were the correct tags, but something like Montclair is not able to get the correct tags. And of course, like there's other examples where you're able to find the right tags with this model compared to the previous ones. Yeah, so this actually was a pretty good example. I think it sort of says hand mixer or something like that. Mixers and accessories, but it's not really talking about audio mixing. Okay, any questions on this part? I'll move on to some RL stuff otherwise. Okay, I don't see anything. All right. So, right, so this was about semantic supervision, which is more on the supervised classification side, right? So we're using language as a way to just provide more information on the output space, but we can use language in other paradigms and other ways as well, right? So I'm sure all of you are aware of, you know, like Lewis mentioned, you know, some of you are doing stuff around RL. So RL, deep RL especially, has seen a lot of successes in the last few years, like the AlphaGo or, you know, the Rubik's Cube demo and so on. But, you know, if you have ever worked with RL yourself, right, this is how it looks like, right? So something as simple as landing a you know, a system within 2 flags takes forever, right? So it's going to try again and again till it succeeds. It's sort of this trial and error method that is very, very inefficient. Or sometimes it can be downright scary, right? So imagine you're training a robot to flip a pancake. Things like this could happen, right? So obviously we don't want these kinds of things to happen when we're training our RL systems. So in general, you know, there's sort of these big grand challenges that people talk about in reinforcement learning, right? So even though we've sort of solved impressive problems with RL. It takes a lot of training, right? It's very, very inefficient. And then there's these questions around generalizability and control, right? So let's say you train your AlphaGo or you train your Dota bot. Does that automatically learn to play chess? No, right? So even though there's similarities in high-level strategies that you could potentially use between these different games, the model doesn't really have a sense of doing that at all, right? In the way that we're currently training them. And then there's also questions around safety, which are popping up more now, right? So if you want to use reinforcement learning for your humanoid robot, you probably wouldn't do that right now unless you have a pretty good constraint on what it can or cannot do, because once it breaks its arm, you're looking at tons of dollars expenditure in repairing it, and the robot is out of commission for a few months, right? So jokes aside, right? So these are sort of like these major recurring challenges, and we need to think carefully about how we can solve them. And what I want to say here with relation to this talk is, language can help again, right here. So humans do learn through reinforcement, but they don't do the same type of learning that an agent does, right? When it's trying to explore a world, right? In fact, coming back to this lunar landing example, while an agent gets several thousands of tries, humans literally got one try to land this, this spaceship on the moon, right? And we did it, right? So how did we manage to do it? At least one critical factor to this success was the fact that they had external knowledge, right? So things like, flat surfaces are stable and probably good for landing your ship. The gravity of moon is different from the Earth, things like that, that help you perform or take decisions without needing to explore and figure out what happens in the first place, right? So this sort of external knowledge, which can obviously be specified in language, can basically helps humans achieve even complex tasks like these that was never done before, right? And so the natural question here is, can we get machines to do the same, right? So can we get our RL agents to, which by default learn from acting in the environment, right? So they learn through experience, they learn by interacting and getting feedback from the environment. But there's a sort of complementary learning process here, right? So humans learn by reading as well, right? So humans learn by reading books, reading the web, reading the manuals, and so on. And the key question here is that, can we get machines to do the same, right? So I'll give you a few examples of projects that we did around the space, where we're basically getting RL agents to learn through a combination of doing, which is interacting with the environment, but also by reading things, by reading knowledge and getting this external knowledge that can help them get a better policy faster. So I'll talk about 3 pieces of work. So the first piece of work is tackling this problem of generalization, right? So this was work with Ani Majumdar and his lab here, folks, students involved were Alan, Bharat, and Jimmy. So the problem that we wanted to tackle here is that of robotic manipulation, right? So in robotics, this manipulation task is quite hard, and this particular task over here is looking at manipulating tools. So think about things like a hammer, pliers, or whatever tool that you want to use, right? And our goal over here was to say that, okay, you can obviously use reinforcement learning to perform several tasks with these different tools, and you can train your system with RL, your favorite RL algorithm. But what we wanted to check here is, can we use descriptions of these tools to help the agent learn faster or adapt to unseen tools, right? So, and this is sort of intuitive to you as a human, right? So let's say I give you a tool that you've never seen before, right? Let's say you've never seen a hammer before, right? Or you've never operated one before. But I give you the tool and then tell you, hey, the hammer has this general sort of property that there's a head that is really, really heavy, and then there's this handle where you should usually hold it, and you try to use the head, right, instead of holding the head and then hammering with the handle itself, right? So that's the sort of knowledge that we want the agent to take, right? So we basically came up with this meta reinforcement learning framework where you can use language as language guidance for generalizing to new tools, right? So during this meta training phase, we train the model to learn to operate these different tools, right? The tools that are seen, but at the same time, give it access to descriptions of these tools, right? So these descriptions are usually talking about the geometrical and utility properties and so on, right? So this basically ensures that the model, while it's learning how to use these tools, also uses a description and associates those descriptions to the properties of the tools themselves. And so once that sort of meta training phase is done, we can then adapt it to unseen tools, basically, right? So we can now have, even unconventional things like a faucet or a paint roller, but as long as you're describing what it is, right? Like what is the shape, what is it, what are sort of like the weight properties and things like that. The hope is that the model will, quickly learn how to grasp the tool, how to push with the tool, or how to hammer with the tool, and so on.
I have a question actually. Did you do any ablations over the text descriptions to see like what parts of the text description it actually uses?
Okay, that is a good question. I believe we didn't really do that. We did some ablation where we used different sets of descriptions just to detect the variance. But
okay.
That's a good point. We didn't. Are you talking about like just basically taking specific sentences out of this and seeing?
Yeah, or just like breaking it down into keywords and removing keywords to see like if you get the same accuracy.
Yeah, that's a good point. We didn't do it, but I can ask Alan whether we can just quickly try it. Thanks.
Okay.
Okay, so that's the high level setup, right? And I'll show you, basically some high level idea of the results. So what we did was we performed simulations using this Frank Honda arm using 5-bullet. So it's a pretty realistic simulation. We just basically have this RGB cameras, and the inputs are 128 by 128. And so we collected these CAD models for 36 different tools, and then we also collected descriptions for each of these tools. And we kept 9 as unseen tools, right? So they're never seen during the meta training phase. And so we test on them. So these are the 9 tools. And then we tried it for 4 different tasks. So pushing is just pushing the particular object to a particular goal location. Lifting is lifting it. Sweeping is using the tool to sweep something else. And hammering is, using the tool to hammer, I think it's a nail inside a particular object. So different kinds of tools. So for each of these tasks, different tools do work better, right? So you can see sort of that variance here. So in these curves, in these bars over here, you're seeing the performance after the adaptation phase. So after we give it some training runs on the new unseen tasks, unseen tools, we can see the final performance here. And so yellow and red are basically the 2 models. We call it ATLA, or like adaptive tool manipulation with language adaptation. So these 2 bars are usually pretty good, right? So I mean, there's some variance depending on the tool, but you can see that it gives you some advantage in terms of the final reward in pushing and lifting, and also the other 2 tasks, but I didn't put them here. But this is just the performance, but the more important part is like the speed of adaptation. So on the right-hand side over here, oh, sorry, I forgot the legend for this. But on the right-hand side over here, the orange curve is basically ATLA, and you can see how it adapts much faster to the reward, the final reward that it gets, right? So it's able to quickly adapt even with a few iterations to using the tool in a proper manner on most of these, right? And so the yellow curve is in most cases higher than the other 2 baseline curves, the blue and the green, which are the other baselines. Okay, so yeah, so the high level idea here is, if you can, if you want a robot to generally use any kind of tool, right, you just provide it sort of a manual, right, or maybe you can figure it out from the web, and that can help us scale it to more kinds of use it for scaling up to more kinds of tools and so on. So that's kind of like the high level pitch for doing this. So okay, so then let me show you a couple of other pieces of work, right? So this was on generalization, but you can also talk about what if we could use language for other things, right? So for example, can we use language to specify safety constraints, right? So you're trying to train your robot and you want it to act in a safe manner, right? So just to set you up for what this is generally falls under, right? So there's this realm of constrained reinforcement learning where people have been thinking about this problem for a while, right? So how do you get agent to learn policies in a safe manner such that you obey some certain constraints, right? So for example, don't step out of certain boundaries or don't fly into windy areas and so on. And the way that people have approached this traditionally has been to specify these sort of constraints in some particular pattern, which is usually a mathematical form, like a logical form or a cost function or something like that, right? So here's an example where you're trying to maximize get the policy that maximizes a return such that the distance of your policy from some safe policy is less than delta, right? So I won't go into details as to what this distance measure is, but you can see even with this sort of specification, right? So you really need expert knowledge to design such constraints, and this is something that a lay person cannot do, right? So this requires some expertise and time, and can be expensive to get these kind of constraints. And so in this case, we ask the question, can you just sort of abstract away such that you can use natural language to specify these kinds of constraints, right? So this is work done by Jimmy and Michael, and I was at last year's NeurIPS. So we basically wanted to ask, okay, how can we use natural language to constrain the policy learning itself, right? So we did a sort of control experiment on a grid world environment. We didn't use a real robot for this, but our goal is the same, right? So we basically said, okay, let's say you have something like this grid, you have constraints like budgets on how many times you can step on a certain square, or how many times how close you can be to certain objects and so on, or even sort of like sequential constraints that tell you what happens temporally, right? So across a trajectory, what are things that you can and cannot do, right? So for example, here, if you step on a grass, you're protected from lava or something like that, right? And so the kind of idea here is, you have this agent that moves around. This is built off of the baby AI environment, if you know that, but it's trying to collect these rewards, right? So the rewards are a key, a ball, and a ladder, but there's these other tiles over here that are related to the constraints that we set. And so I want to quickly point out, you might be thinking, okay, how is this different from instruction following? So first of all, the constraints are auxiliary, right? So they don't really relate to the goal of getting the rewards. So you can totally ignore the constraints and still get all the rewards. So these are two different things, right? And that's true of your robot too, right? So let's say your robot's goal is to, go get you the can of soda or something, right? It can break everything in its path and come back with a can of soda, and it has accomplished its goal, right? So these are two different things. Constraints are basically auxiliary, and the rewards are not correlated with these constraints. And the more important thing is, like, once you get the agent to understand these constraints, you can do different tasks as well, but apply the same set of constraints, right? So let's say tomorrow, or I guess in the test set, which I'll show you now, I change this to a green ball. I can use exactly the same set of constraints, and the robots should still be able to find the green ball while respecting the constraint that I set, right? So basically, constraints in one sense can be more general, right? So you can say, even for your own household robot, you can just say, hey, I don't want you going near the TV, whatever you do, right? So, and that sort of generalizes across different tasks, whereas rewards are more, or instructions are more specific for that one task only. So yeah, so basically, we first sort of collected a benchmark around this, right? And our approach is actually quite simple, right? So we call it POCO, our policy optimization with language constraints. So we don't really, you can't really, or I can show you the results, but you can't really simply stick in the constraints as like an instruction and hope the model will solve it. You need to go a little bit deeper. So what we did was we first embedded this constraint interpreter, or we use a constraint interpreter to convert these constraints into tensor representations, and we have sort of like a safety training meta phase to do this. And once you do that, you can then combine this constraint interpreter with a standard algorithm for policy learning. So these can be constrained policy learning algorithms like CPO or PCPO and others. And you can then embed these constraints into the learning process itself, right? So in instruction following, it's sort of just an additional input to the system. But what we're doing here is we're basically embedding or converting and getting these constraints and then embedding it into the policy learning process itself. And then what we basically do is, we get these constraints again just by crowdsourcing them and getting MTurk workers to do it. So the high-level setup is basically like this, right? So there's a safety training phase, the meta training phase 1, where we assume that you can sort of violate these constraints and it's okay, right? So you can think of it as a simulated environment or something for your real robot. And so during this time, the robot is trying to, or the agent is trying to learn this constraint interpreter and the policy network such that it can interpret these natural language constraints, right? So over here, we're not caring too much about, during the training phase, we're not caring about how many times you violated. But during the safety evaluation, that's where you're learning a new task. But at that point, you want to make sure that you obey the constraints as much as possible. Okay. So, right. So like I said, the analogy for this would be something like, think about the safety training as happening in some simulator where you're grounding the language and learning how to interpret the constraints. And then once you're done with that, you deploy it on a real robot or something that's just trying to learn a new task. And then use these constraint interpreter that you've trained to sort of constrain how the robot acts. Okay, so I'll just give you a quite high-level summary of one result, right? So we have this benchmark called Hazard World. It has many different maps and environments, but one snapshot here is basically showing you the reward as well as number of constraint violations. The left is the reward and right is the number of constraint violations. And we have a bunch of different baselines. So RW is just a random walk baseline. It just shows you that getting the reward is not trivial. And then CF with PCPO is basically a an instruction fusion model, which is just basically saying, okay, just take a standard instruction following model and optimize it with PCPO. This is another baseline that's doing a similar thing, except it doesn't even care about the constraints, right? So it's just using TRPO, a standard algorithm, to modify this to learn the policy. And POCO is the method that I described. So you can see, reward-wise, the TRPO algorithm is probably second best, but we still get a much better reward. But once you go to violations, right, TRPO and random walk, because they don't really care about the constraints, they perform pretty bad in number of violations in each episode, whereas POCO is probably the lowest across these different models, even though it's not perfect, right? So there's still room for improvement in terms of, so this is sort of like looking at just average constraint violation, but there's more recent papers now that look at, worst case constraint violation. And so making that sort of tighter in that, it could be a potential, avenue for future work. Okay, so basically the idea behind this project was to show that, okay, if you can sort of train these models to understand constraints, then you can get end users or people who are actually interacting with these agents in the end use case scenario can set up their own constraints in using just pure natural language. Okay, so let me just show you one last piece of work, right? And then I can take questions. So one question that you can ask is, what about language models, right? So when we think of agents now, there's sort of like this blurriness happening, right? So language models in some sense can also be thought of agents, right? And so we ask a similar question, right? So this is ChatGPT again, so it's making a second appearance, right? So do language models have similar sort of properties that can be helpful to constrain, right? So in this example, we ask it to talk about Newton, right? So it talks something about Newton, right? And then if you ask it, now talk about somebody with a similar background, but do not mention any physicists, right? And unfortunately, it just goes about talking about Albert Einstein, right? So even with all its impressive generation capabilities, we can see, right, a state-of-the-art model is not really able to follow a simple constraint that says don't talk about a physicist, right? It even says Einstein was a physicist, so it's not really thinking that Einstein is not a physicist or anything like that. So we tried to, so in order to solve this problem, we came up with a benchmark on a model. So this was work led by Howard and Hui Han. And so we call this the Cognac benchmark, and the Cognac basically stands for control generation with natural language constraints. So again, the idea is similar to what I talked about before, right? So we basically want to train language models such that they can understand constraints in natural language, right? And the reason, again, it comes back to my earlier motivation, right? So if you want to fix models on the fly, the easiest way is to describe what we want the model to do and what we don't want the model to do, right? And so we came up with this benchmark called Cognac. It is based on it's a benchmark that's trying to evaluate text generation with natural language constraints, and it's based on data sets that are constructed from structured sources. So we used WordNet and Wikidata, which allows us to evaluate whether the generation constraint conforms to a constraint or not, right? So here's an example of one such task in this data set, right? So if you ask it something like talk about a motor vehicle and give it a few prompt examples, right? A cruiser, motorsport, gas guzzler, and things like that. And then you ask it at the end, do not talk about cars, right? And then the model then generates after this, and we can then evaluate whether it's talking about a motor vehicle, that is it's on topic, and also that it avoids talking about a car. And a similar thing with something like this, right? You wanted to continue talking about people who are citizens of UK, but do not mention any politician, right? So that's sort of the setup here. Okay, so we then, we develop a data set for this. I won't go into too much detail, so you can look at the paper. And then we also develop an approach that works for this particular task. We call it Cognac Gen. At the very high level, what this is doing is using the language model itself to basically guide its own generation, right? So this language model is frozen and it's generating text that is conditioned on the constraints and the instructions. But there's another language model which is basically prefix tuned to understand the constraints, and it provides some sort of logic adjustments such that the original language model conforms to the constraints itself, right? So we call this distilling self-guidance. It's a very simple technique, and all we're doing is prefix tuning to make sure that you're understanding things like, do not mention any politician, and how that translates into the distribution over the tokens that you're actually generating at each time step. And the whole thing is that, at inference, everything is simple in the sense that, you just have to do one pass. There's no re-ranking or anything like that. In one pass generation, we're able to, generate text that does somewhat better at following constraints. Okay, so very quickly, let me show you some results, right? So this is on our data set, right? So you can see GPT-2 XL and GPT-3 were two baselines. You can just focus on the IC score over here, right? So it's just looking at correctness. You can see even a model such as GPT-3 doesn't really conform to the constraints that we set up, whereas Cognac Gen is able to do so. There is one caveat, right? That instruct GPT somehow actually is slightly better, and it does better on the IC score, but still far from the max score that you can get, right? Like it's just 100. So you can see that first of all, it's slightly better, but one caveat again is the size of the model is way bigger than what Cognac Gen is, right? So Cognac Gen is based on GPT-2 XL, but I'm pretty sure if we had access to GPT-3 and we could do prefix tuning on top of GPT-3 or even instruct GPT, we'd be able to go much higher. It's just that we don't have access to that. But the technique should carry over in terms of generating text in a constraint conforming way.
So the instruct GPT model there, which that was like text DaVinci 03, I guess.
I think it was DaVinci 03. Yeah.
Okay. Yeah, because there was a lot of confusion with that recently. No one knew like which one was actually instruct GPT.
Yeah. So yeah, we should probably put this as a DaVinci 03. Yeah. Yeah, we haven't tested with ChatGPT, but I guess that was that was right after we released this. Okay, great. So to sort of summarize, I hopefully give you an idea of like how you can, use language to guide machine learning in different ways, right? So on the supervised setting, you can use it to specify different parts of the modeling setup, like semantic supervision. But you can also use it for RL agents, right? You can use it to provide extra guidance, specify constraints. I didn't talk about some other work. You could also use it to, give feedback, but that's more in the nascent phase of things. So there's very, very different ways we can think about using language. And I think it's actually going to be if we are to scale up, some of these ideas around reinforcement learning and large language models, we do and make them more democratized, right? And involve the end users in being able to personalize systems, but also, fix errors and be able to adapt on the fly. We need these systems that can be trained with language supervision, right? So hopefully, future work can sort of build upon these and also think about different ways of doing this, factorizing the different types of information that are used, use more contextual and perceptual signals from visual input or things like that. So I think it's exciting. Let's see how things play out in the next few years. But I think I'm hoping that we can see more interesting things coming out. So with that, I'll stop. And thanks to all the collaborators. And if you want to look at any of the papers, it should be on my website or on our lab's website. But just email me if you can't find it, and I'm happy to send it. Thanks.
Thank you. That was a great talk. We can do you have time for questions?
I have a question on why you train on a 1.5 billion model. Do you have a constraint? Yes, this one. Is there a constraint or accessibility of bigger models?
Yeah, absolutely. Yeah, I don't think we're able to, I mean, this was based on GPT-2XL. We're not able to really train, well, okay, so you may ask, okay, we could have trained maybe slightly bigger, but we actually started this project a while back. We can try it with a 6 billion model maybe, but I don't think we can go much bigger than that given the GPUs that we have. Is that your question, like going higher?
Yes,
I don't
yeah,
think
no, just
1.75 billion.
Yeah, no, because I remember I read that extract GPT or like chain of thought effect happened after 100 billion parameter. It's not confirmed, but I read this line that stuck in my mind, and so that's why.
Absolutely, yeah. If there's a way to try it with 100 billion plus parameter model, that would be great. Like, I don't know if anybody here has access to something like that would help train that. We would absolutely love to try it.
And the second question is about the CLIP initial model. Is how fast is the training? Can we get to the point where the insertion of a new embedding from a description arrives almost at real time?
Yeah, so the training is not really that much slower because you can already pre-compute some of these things, right? So all you have to do is like sample descriptions, and that's pretty fast as long as you have threads that pull it in, just like the batching process. So it doesn't really slow down either in terms of runtime or even in sample efficiency. I don't think there's a big difference.
So once you sample the once it's trained and you want to create a new description to add to the search phase.
I see. Okay, that could be depending on how you do it. So if you want to do it on the fly and get it from the internet or something, I guess that would add some latency. But the assumption here is that you for your test classes, even though they're unseen, you already know what those classes are, and it's a one-time thing. You just have to scrape it once, and you're done with it. So I don't know if you're thinking of something more dynamic than that.
Yeah, like that's I really like the intuition of having the description to guide the search space, right? And so right. giving some search space, and I say, okay, how fast can we have this feedback from the user, right? And so it's like, can I add the more embedding as we talking? Yeah.
That's a good question. Yeah, I mean, sort of connecting this to some kind of human in the loop system would be interesting if there's a way to do that, and getting users to just on the fly change descriptions or something like that.
We're doing human feedback from in Carper AI, so that was like all the train of thought.
Right. No,
Thank-
that makes sense. Yeah, I would love to chat more around that.
Thank you.
So I wanted to know what your opinion of the Sparrow paper was from DeepMind, where they had like a preset set of rules, and they asked human annotators if a chatbot violated the rules and where and how it violated it.
So which part do you want the opinion on?
Well, just how it compares to your method. I guess the one of they seem very complementary, but I just want to know like where the compliment was almost in your view of them.
Yeah, I think, well, correct me if I'm wrong, but it's still a fixed set of things that they provide, right?
Yeah, but there's been like Anthropic work after that where they removed the fact that it's fixed. The oh my god, what was the one right before the constitutional AI paper? I don't remember. Anyway, there has been some work on that, removing the fixed limit.
Yeah, so I do think it's complementary, right? Like, so you're sort of providing some instruction to the human and asking them to score along those dimensions. Yeah, I guess this would be thinking about the human providing language instruction to the agent directly and sort of shifting that comprehension part into the agent itself. So again, I think there is the human feedback aspect of it, right? Like humans can provide instruction through natural language or feedback through natural language. But a more scalable thing I actually think is think about all the knowledge that's on the internet, right? So this is something that the live human doesn't have to be around to do it, right? So if you can get an agent to just retrieve relevant information and then use that for a task, that could scale things up much more, right? Like, so if you think about your robot, it needs to learn to perform a different kind of task. If you can just like Google, find a few articles, let's say recipes or something, right? Find a few articles and then basically just plan based on those high level ideas, that would be very useful.
That makes sense. Does anyone else have a question?
I have a quick question. Is like in the intuitive sense, how sensitive would these kind of techniques be to the actual embedding of the text? Like if you embed the text in some like really naive way of just like, oh, it's just a string of tokens and it's not processed at all, then I would imagine it can't perform that well because it's not that useful. But if you were in some scenario where just embedding the text in a larger space, or like as the text encoders improve, all of these other techniques improve for free just because of the higher like richness of that would be really, an amazing spot to be in, because it's like free gains just for having a larger text encoder or a deeper text encoder or something.
Yeah, absolutely. Yeah, I think that is true. So even with the Samsung thing is just a framework. You could really use any kind of encoder, and the encoder actually makes a difference. I didn't talk about it because it's sort of like a ablation. But yeah, if you just use glove embeddings or something like that, it does perform worse because you're not able to capture the contextual nature of these descriptions. But I agree, like probably even representations that do a better job of taking these different pieces of information about a class. So all we did is like literally just sample different things and average it. It's the naivest thing ever. But if you're sort of smarter about how you encode the different pieces of knowledge you have about a class, I'm sure you can do much better with just the overall framework.
So you're saying one could just simply learn differentiable self-attention model on these embedding sets and learn it end to end with the RL feedback.
Yeah, that could be one way. Yeah, I mean, I wasn't thinking specifically of attention, but I was even thinking simpler, like a weighted thing. But yeah, you could even learn.
Yeah, I mean, attention is a fancy way to say weighted things that come out of an output of 3 layers, probably.
Yeah.
What we do in like on medical images a lot, like to scale down the resolution such that the whole image level label is able to propagate into the sub-image representation.
Yeah, exactly. I'm guessing you mean something like condition on the input. You attend to the most relevant part of the text or something.
Yeah, well, and maybe some of the embedding of the text itself, right?
Yeah, that would be very interesting. Yeah, I would be curious to see if that does better.
Last call for questions. Okay. Well, thank you. It was a great talk. We've certainly all enjoyed it. Tons of interesting discussion. Yeah, thank you for coming out today.
Sounds good. Thank you all.
See you guys.
Thank you.
Bye.